our third talk, Andras Stipsicz, and here for homology, right?
Yes, so in the morning I made an attempt to sort of raise questions and tell you some details about Sargent-Whitney theory. That's very effective. It is really the relative study for manifolds, although when you consider the same equations on a three-manifold cross R, you can derive three-manifold invariants as well. Now we take the opposite route, and we will do something for three manifolds and then derive a four-dimensional invariant. And I will be, again, very sketchy, but I hope I can convey some of the ideas which go into this theory. And I would like to focus on one theorem, and we will see whether I get there. So, whenever you would like to define an invariant of an object, you should present it in some way. So in this theory, three manifolds will be presented by Hegar diagrams. So we consider a genus G closed oriented surface and a vector recollection of simple closed curves, actually two collections of those. So these are disjoint simple closed curves. These are disjoint simple closed curves. And the way they intersect each other, that's really what we would like to measure. And there is one condition we would like to, there are some conditions we would like to satisfy. If you delete from sigma all the alphas, this should be connected. And when you delete the betas, it should be also connected. So that's our input. And the way you should think about it is that we take sigma, unfortunately it will be now a line, and we promote it to a three manifold. So this will be sigma cross -1, 1. You copy all the beta curves up here. This is, this sigma cross 1 is a copy of sigma, and you copy all the alpha curves down there. And now we just take three-dimensional two handles, which are just like a breakfast bowl, and we just turn them upside down and glue them along the betas. And then we don't turn them upside down, we just sort of glue them from the below along the alphas, and we get a three-dimensional space. And this condition and the number of curves compared to the genus will ensure that this new boundary will be just S2. And then we just close it up, and we close it up down here. So what happened is that starting from sigma alpha beta, we constructed a three manifold. This is an oriented closed three manifold. And here are two facts. Every y, and then now y should be closed and oriented, can be presented this way. So it's not a very specific construction. You can reach every closed and oriented three manifold. And the presentation is unique up to three moves. And I will not detail the moves, but these are very much like Reidemeister moves for knot diagrams. The name of the moves are isotopies, handle slides, and stabilizations. So what we would like to do is to create some, or to associate some invariant to this triple in a way that it doesn't change when we apply one of these moves. So what doesn't change the three manifold, and at the end of the day, we will get the three manifold invariant. So this is the plan. This is not exactly what will happen, because we have to pick an additional point. So what we do, we consider this four tuple, where this is just a point in the complement of the curves. And we associate to it a much higher dimensional space. Namely, we take the symmetric power of the surface, and we should stop for a moment typically a symmetric power is a very singular space. You have to remember that this is just the product of G copies of this surface, what I'm writing, divided by the action of the symmetric group, which is a non-free action on this high dimensional manifold. But it happens to be true that if sigma is a two-dimensional manifold, then this will be a 2G dimensional manifold. This is the instance of the fundamental theorem of algebra. And for these alphas and betas, we just take their product. So these are, all the alphas are just circles. So these are G-dimensional tori. And since we are viewing them inside a symmetric power, it doesn't matter which order I'm considering. This will be just two complementary dimensional G-dimensional tori. And for W, we associate VW, which is just those elements in the symmetric product which have W at one coordinate. So remember that elements here are just G points, potentially with multiplicity in sigma, and we just take this divisor where at least one slot is occupied by W. Okay, so this is the higher dimensional situation. And then it turns out that, again, a fact, the symmetric power admits a symplectic structure for which T alpha and T beta, the two tori, are Lagrangian. And whenever you have a symplectic manifold and two generically intersecting Lagrangian submanifolds, then there is a method to associate groups or chain complexes to this, and this is what we will follow. I said that they are intersecting transversely. This follows if we assume that these guys intersect transversely, and we will always assume that. And so the chain complex, so I will be very quick here. So pick sort of a base ring, which can be the field of two elements, the polynomial ring over the field of two elements, or actually the space of Laurent polynomials, or sometimes this formal power series. And they will all give you different theories, and I will sort of comment on why do we need all these. And so define CF, and we need a decoration here depending on which base ring we take. This will correspond to hat, this is like minus, this is infinity, and there is no decoration for that. This is like boldface. So, and this circle will mean that I just pick one of those, doesn't matter which one. Will be the free R module generated by the intersection points of T alpha and T beta. So you have to remember again, this is a real 2G dimensional symplectic manifold. These are two transversely intersecting G dimensional submanifolds. Everybody is compact, so there are finitely many intersection points. We just take this finitely generated R module, and this is our module, and we take a boundary map from CF0 to CF0 by counting holomorphic disks. So I will not be very specific on how to do that. I just remind you that, so this is generated by intersection points xn, x1 up to xn, and so we have to specify what is the coefficient of xj in data xi. This is the number we would like to specify. And so the rough idea is that we have this symmetric power. We have the two intersecting Lagrangian, oops. And we have these 2 points, xi and xj. And then we are looking for disks, which sort of maps from the disk in the unit, in the complex plane, the unit disk, in the complex plane, where minus I goes to this xi, and this I is completely different I than this one. And then this point goes to there, the left-hand arc goes to T alpha, the right-hand arc goes to T beta, and otherwise it's not only a continuous map, but it is holomorphic. In order for this to make sense, of course, it's not enough to have a symplectic structure. We have to pick what we called last time an almost complex structure on this manifold. So this plus J almost complex structure. And this gives us an endomorphism of that modulo, almost. Because there is this W, and we never use that. And this will sort of distinguish all these choices. So now I use a color. So there is this VW inside. We have to remember that, so this is of dimension 2G. This is of dimension 2G minus 2. And the disks are, of course, of dimension 2. So generically, the disks intersect this VW in some number of points. And we get this theory if we just demand this intersection number to be 0. We get the next theory where we do allow the two manifolds to intersect, but this intersection number is counted in the U power. And this is what we do for the rest of the cases. So this was very vague, not very vague, but very quick. And I hope it only, some of you was just, for some of you, it was just a reminder. I was thinking of like asking at the beginning, like who is familiar with that, but I then decided not to. Was it a good idea? I don't know. Okay, an extra little detail. So, okay. Little fact, an intersection point X and W determine a spin C structure on the three manifold associated to the diagram. I will not tell you how. This is a spin C structures on three manifolds are somewhat tamer objects that in 4 dimensions. They correspond to lower zero vector fields, and then you can interpret an intersection point as gradient flow lines from index 2 to index 1 critical points. This W can be interpreted as a gradient flow line from the maximum to the minimum of a certain Morse function. And then you just do some magic to turn that into a nowhere vanishing vector field, which happens to be a spin C structure. Again, if you heard these words already, that it should resonate. If not, I'm not sure that it's so helpful. So definition, HF, again, the circle of Y is just the homology of the chain complex CF circle with this boundary map, where the boundary, probably I should also put a circle there. Again, it depends on which base ring we pick. And then the theorem. So this notation is sort of suggests that although we had to make all kinds of choices, what are the choices we had to make? Well, the Hagar diagram representing Y, and then this almost complex structure which allows us to consider holomorphic disks. But at the end of the day, the HF circle of Y is an invariant of the underlying three manifold, and it splits according to spin C structures as follows. So HF hat Y is just the sum of HF hat of Y equivalent with the spin C structure, where the chain complex computing this homology is generated by only those points, those intersection points which admit this particular spin C structure. Notice that there are like finitely many intersection points as we agreed, but there are many three manifolds which admit infinitely many spin C structures. So what happens is that for most of them, this group will be just zero. Okay, so this is the package, and here's the first. Okay. In my view, there are like three important theorems to start the theory. The first is that what you get is really an invariant of the three manifold. This relies on some ideas of Lagrangian Floer homology. For example, the invariance, the independence from the almost complex structure is a generic feature of this whole package of Floer homologies. It turns out that the independence from isotopy and the Handel slide also can be packaged into that. What should be a surprising fact that it does not depend on the stabilization. So if you take a diagram and you stabilize, then the invariant will be, the homology will be the same. You should be surprised by that. I hope you are. You are doing this operation in two different spaces because you change the genus. So you change the ambient space, you change the genus of the tori. So that should be a surprising fact. And so that's the first important theorem, that we do have an invariant. The second one is what I really would like to talk about today is the surgery exact triangle. And the third one is that there is a version of this theory for not only for three manifolds, but for three manifolds containing knots or links. And it turns out that the topological input is not very different from what we already saw. So instead of having this four tuple, the surface, two sets of curves, and a point, you have to add one more point. And this sort of influences the boundary map, and it gives a little bit of a complication, but there is a nice relation between the knot invariant and the three manifold invariant. So this theory is very much well designed for surgery-related questions. Unlike Seiberg-Witten theory, where this is really a pain in the neck to actually come up with knot invariants. You have to pay for it, of course. It's very topological. So for example, it's much harder to take advantage of analytic structures like a complex structure of four manifold. This theory just doesn't see that at all. Symplectic one, I will talk about that a little later. But if you are interested in analytic questions, you should go to Seiberg-Witten. If you are more in a topological framework, this is your theory. So this is a relation to knot Floer homology. So as I already mentioned, I would like to spend a little time on this surgery exact triangle. But before doing that, I will quote one theorem. So here is the theorem. Yeah, so I didn't mention names. I did mention Hegard and Floer, but so this whole story was designed and perfected by Peter Oswald and Zoltán Szabó probably safe to say in the past like 20, 25 years. So when I just take a theorem and I don't attribute it to anybody, this is the reason they did it. Okay, so maybe that's the convention. You just put it O and S. That's the beauty of Hungarian language. This is one letter, although it looks like two. So here is an oriented surface and closed of positive genus. Then we have an adjunction type inequality, and it goes as follows. If HF whatever of y in a certain spin C structure is not vanishing, then when you take the first Chern class of this spin C structure and you evaluate it on the fundamental class of this surface, then this should be less than or equal to twice the genus -2. So this should be very familiar. It looks exactly the same as we had it before. This was the basic class. This was the class where the Seiberg invariant was non-zero, but everything was set in a four-dimensional setting. So the surfaces might have self-intersections. This is not possible in three dimensions. So there is this missing f dot f, which would make no sense. So this is sort of the adjunction inequality in this setting, and we will make use of that. The proof is not very complicated. In fact, what we can do is we can come up with a Heegard diagram where the surface sigma almost contains F. So F decomposes like some subsurface plus two disks, and we can pick the Heegard splitting or the Heegard surface sigma in such a way that F naught sits in the surface, and these guys are just disks which you get by attaching along one alpha and one beta. Sorry, one beta and one alpha. Okay, so that's the name of the game, and then of course we have to make sure that we understand how to compute the evaluation of a spin C structure of this first Chern class of a spin C structure on the surface, and that's the proof. I will not go into the details, but this is something very useful. And instead, I would like to spend some time on sort of convincing you that the surgery triangle is a useful tool. So first I should explain what it is. Okay. And for that, I should introduce the concept. So definition. So how did I phrase it? Alpha, beta, gamma, simple closed curves in the torus form a triad if they meet pairwise in a single point, and we can assume that with sign -1. So we can orient these curves in a way that they meet once pairwise, and the signed intersection is always -1. So I will just draw an example for that. So I will use this hexagon as the model for the torus. So this is identified with this side. This is identified with this, and this is identified with that. And now I will try to use colors. So this is my alpha, and this is my beta, and yeah, this is gamma. So suppose we have a triad like that, and I hope I got the order right. So if you take alpha and beta, then you can pick the orientation so that the intersection point is negative, and then beta gamma also negative, and alpha gamma is negative. Okay, so a triad of manifolds So suppose that M is a compact oriented three manifold with a boundary being diffeomorphic to the torus, and put a triad of curves on this. So we can create in this way three manifolds, closed three manifolds. So attaching 3D two handles to alpha, then beta, then gamma, and the 3D three handle, we get y alpha, y beta, y gamma, right? So we have this three manifold M, which has a toric boundary, and we have the three circles, alpha, beta, and gamma, as I drew it here. And first I attach a three handle along alpha, then along beta, then along gamma, and I close up these three manifolds to get closed oriented three manifolds, and we get this triad of three manifolds. And now the theorem is the following. So if we have a triad of three manifolds, then there are maps. What is the name? I don't know. Fi such that HF y alpha, y beta, y gamma. So this is F1, F2, F3 is an exact triangle where this circle is now can be hat or plus, which I will define later. So this triangle does not apply to every dialect of the theory. It applies for hat and for plus. I will explain what plus is. And what does it mean to have an exact triangle? Well, we have these consecutive maps. So it just means that the kernel of F1 is the same as the image of F3, and so on and so forth. Okay, question?
Do you need the boundary to be a torus?
Did I say that? Yeah.
Can't you do the same thing with a genus G surface with like a triad of curves?
I'm not sure I'm following you. What happens with the other genus? So what happens with the other curves?
Like take a genus G surface and you have G alpha curves, G beta curves, G gamma curves, such that like the three pairs of them.
No. That maybe, yeah, I don't know. I don't know how to put that. You cannot put them in one triangle. You will see.
Okay, just repeat that fact again, on the board, what section?
Intersection.
Intersection point.
An intersection point, like these two guys intersect each other and you get the point of the intersection. Sorry. Yeah, my handwriting is like, you know, it used to be nice. Exchange. Okay. Yeah, so here is an example of that situation. So yeah, the best is to erase it. Example of a triad of manifolds. So you just take a three manifold Y, which contains a knot with a framing. then what you can do is you just take the tubular neighborhood of this knot and take it out, and that will be my candidate for M. This will be a compact three-manifold with T2 boundary. Then you can sort of reconstruct Y, or we can take the Serger manifold with surgery. So this is not how we denote it, right? YKF. So we just take the surgery with that given framing, or we can just take the framing plus the meridian. The new framing will be one more twist and the same knot. And it's not hard to see that somehow in the torus, in the boundary torus of when we get the complement of the tubular neighborhood, the meridian will be my alpha, the framing will be my beta, and this will be my gamma, and they will form a triad. So the surgery exact triangle tells us that if you have a manifold with a knot, then we take the invariant of the manifold. Then we take the invariant of the Serger manifold, and then we take an additional surgery, then they will fit into a triangle. It doesn't look like a great theorem because it doesn't compute you the effect of a surgery. That would be fantastic to get a formula for this guy in terms of, say, Y, right? That's like just too much to hope for. You know, we learned it in homological algebra that formulae are for Euler characteristic and for algebraics, and we have long exact sequences. That's what we have. So this is like sort of a wrapped up long exact sequence. Okay, so how can we prove a statement like that? So I will give you a homological algebra statement, and then we should see whether it applies in this present context. Okay. So here is the homological algebra. So suppose we have three chain complexes, Ci delta I for I1, 2, 3 are chain complexes. Together with Fi going from Ci to Ci plus 1 chain map. So, you know, I is counted mod 3. So from C3, it goes back to C1 again. And what else do we need? HIs are from Ci to Ci plus 2 chain homotopies between the zero map and Fi circle Fi plus 1, i.e., we just have this equation that delta I plus 1 Hi plus Hi circle delta I is just Fi circle Fi plus 1. Okay, so this is like these Fi's will generate my capital F's. The second sentence tells us that if we do two steps, then the map will be actually chain homotopic to the zero map, meaning that the induced map, the composition of two consecutive guys, is actually the zero, which means that the kernel of this one contains the images of the previous. So those are somehow very reasonable expectations. The third one is a little less so, but we need that. Phi I, which is just Hi plus 1, Fi plus Hi Fi plus 1 is chain homotopic to the identity on Ci. So suppose that we have this situation then the conclusion is that these homologies of these chain complexes fit into a surgery triangle. So I will continue it here. Then homology of C1, delta 1, homology of C2, delta 2 is the map induced by F1. So this is an exact triangle. Okay, so let me just try to make a picture so which helps you to sort of not memorize, but at least to digest what's here. So we have C1, C2, C3. They have their own boundary maps, of course. And then we have the Fs, they just go around, F1, F2, F3. We have the ages, which sort of go in the opposite order. So we have H1. This is the indexing I use, I don't remember. Yes, H1, H1, H2, H3. And then these phi i's are just maps like this. They just give these funny ears. And so there are like how many? 9 maps, and they satisfy these conditions. Then a not so complicated homological algebra argument proves this statement. So what we are left with is to define these 2 sets of maps and then check this condition. Right? And of course, I will not do it completely, but I will give you an idea how to define the Fs and maybe sketch how to define the H's. Okay. And indeed, the definition of the FIs, well, this requires a little bit of thinking of what happens if we have 2 3-manifolds and a cobordism between them. So as customary in these circles, whenever you see a cobordism, a 4-dimensional cobordism, you would like to chop it off into handle attachments. You can attach first the 1 handles, then 2 handles, then 3 handles. And I hope you all got used to the notion that 1 and 3 handles are not exciting at all in 4-dimensional topology. The 2 handles contain all the interesting information. So there we would like to take a W cobordism from Y1 to Y2, want to have a map from HF of Y1 to HF of Y2. And so the way one can define such a concept is to decompose W into 1 handles, 2 handles, 3 handles. And we do something standard here. As the attachment of a 1 handle requires no further choices. You just attach it to the 3-manifold and you will always get, no matter how you do it, you will get diffeomorphic image results. The 2-handle attachments, however, are interesting. So I will only consider those. Actually, I will consider 1 single 2-handle. So we have this Y1, which corresponds to this, this Hagar diagram. And I claim that what we can do is we can choose so that Y2 will correspond to almost the same Hagar diagram, except there is a beta prime. If this was beta 1, up to beta G, then this is just beta 1, beta G prime. So all the alphas match up, all the betas are the same, and the last beta is something new. This can be again retaught by following the same argument I had before. We just take the two-handle attachment. We have a single two-handle. It is attached along one curve. We take the complement of that curve. So this is just y1 minus the tubular neighborhood of the knot. And we take a Haggard diagram for this complement. And then the two last curves will tell us which one is y1 and which one is y2. If you glue back the two handle along the meridian of the knot, you get y1. And if you glue it along the prescribed framing, then you get y2. Okay. Okay. So this just means that now we have like 3 tori in our symmetric power. So this gives 3 tori, T alpha, T beta, and T beta prime. And on the nose, they are not really transverse because I kept the same betas here, the first G minus 1, and I changed the last one. So we have to perturb these betas a little bit. And so now we have 3 tori in the symmetric power. T alpha, T beta prime. For those of you who spent some time with trisections, this should resonate a little bit. So these are like a trisection type decomposition of a cobordism which only has one single two handle. So if you do it for a closed four manifold, then you get something resembling to a trisection diagram. So once we have this, of course, we can consider now slightly different maps. So instead of having the maps, again, we have a symplectic structure, plus we pick an almost complex structure, and we can do it in a way that they are Lagrangian submanifolds. So we now run the previous program, but instead of considering holomorphic disks, we are considering holomorphic triangles by picking 3 intersection points, one from each pair of Lagrangian tori, and then we just map this with the similar boundary conditions, which I will not explain. This gives a map from CF circle of alpha and beta, tensor CF circle of alpha and beta and beta prime to CF alpha and beta prime. And it turns out that this thing is very simple. The corresponding 3 manifold is also very simple. It will be some connected sum of S1 cross S2s. So this chain complex contains a distinguished element. Let's call it T. And so at the end of the day, this W will induce, this one single two-handle attachment will induce a map from this group to that group. This is exactly what we would like to have on the homological level, of course, by sending an X and a T to this Y, to some linear combination of Y's, where the coefficients are taken exactly by counting the holomorphic triangles. Now, this doesn't look like a triangle, but it is, like it's a, okay. And of course, again, we have to pay attention to this divisor, the W, which is lurking in the back, depending, either disqualifying disks intersecting in it when we have the hat, or counting how many times we intersect it when we do the other theories. Question?
What do you mean with the CF alpha beta? What is
so maybe I should add the sigma. So this is the the Hagar diagram using these two sets of curves, and this will give us y1, this will give us y2, and this will give us some auxiliary manifold, which happens to be very simple. In fact, in this case, it will be just the connected sum of S1 cross S2's G minus 1 times. And this has a prescribed element in this chain complex, and we use that to make the map. Does that make sense? Yes?
So far, does this apply to all of the flavors or just cat and spot?
This applies to all flavors.
Okay.
This and we do need that. Okay, so and in fact, now it is this lemma, but these my little FIs are exactly the maps which you get by applying this principle to the triad of these curves. So instead of proceeding any further, we have these FIs. Let me just mention one theorem, one construction. How do we get four-dimensional invariant out of this story? So how to get so the first inclination would be question.
Oh, sorry, you mentioned this connect sum of S1 cross S2, but can you repeat that? What you said about that?
So this pair of, so this is again a three manifold, right? And that will be just diffeomorphic to that.
Oh, okay.
Yeah, so I just wanted to tell you that this one does not carry much information, what this group is. We just pick one distinguished element and we use that to map from here to there. So although it looks like a two variable thing, but one of them, we don't care. We just fix one element here. Okay.
How is the input triad alpha, beta, gamma related to?
Say it again.
I think we took as an input the triad alpha, beta, gamma.
So the input was different, right? It was a cobordism. So it was alpha and beta for y1 and alpha and beta prime. And now I can rename it to gamma if you like, but that's my gamma.
No, but you had an alpha, beta, gamma before when you're describing the triad. The single curve, single alpha, single beta on the torus boundary.
Yes, so, okay, then I will just rewrite it. So this is my gamma. So the alpha is the same. The first G minus 1 betas are the same in both. And the last guy is beta and gamma, beta G and gamma G. Okay. Okay. So how do we get a four manifold invariant? So the first idea, the simplest one, unfortunately it doesn't work. But nevertheless, I tell you. So this is how I thought we should proceed, and then I realized it's stupid. So you have this four-dimensional manifold X. It's a closed four manifold, and you would like to get something very similar to the Seiberg-Witten invariance. Notice that in Seiberg-Witten theory, you sort of treated it as a whole. We picked the metric, and we wrote down a PDE, and we never chopped it off. And we just stopped doing that. We just take it into pieces. We puncture twice. So we have a cobordism from S3 to S3, and then we can just use these ideas just to slice it up to one handles, two handles, three handles, and so on. And then we get a map from S3 to S3. So at the end of the day, X will induce a map like this. And the bad news, and this is what would be very natural. This would be what we would call a TQFT, like a topological quantum field theory. And it is. And it always gives you zero. So it's not that, yeah, well, depending on your expectations, of course, but this is not so exciting. So this is not what we should do. And it turns out that in order to get this, the interesting invariants, you have to consider what we can call like secondary invariants out of the theory. Namely, Remember that we had CF minus, this was over FU. And this can be considered as a sub module of HF infinity, which is U inverse. So these are polynomials, these are low-norm polynomials. This is an embedding, and we can take the quotient. I promise you that I will at least define what CF plus is. This is a theory over the quotient. And the lesson is that in order to find an interesting invariant, you have to use both the minus and the plus theory. And I don't know how do I do with time. I will draw one more horrific diagram, and then we are done. And the horrific diagram is the following. So we have to cut off or four manifold by a middle guy into two pieces. And we consider the following. So we take HF and S3. This is, maybe I will just denote them first S3 and second S3. And S3. And then again, that's our good old homological algebra memory. If we have a short exact sequence of chain complexes, it induces a long exact sequence on homologies. And I do the same for the Y. And then for the other S3. We are almost done. So, and one more step is missing here. HF infinity, HF infinity, and HF infinity. And we need some property for this Y. And what the property we need is that the B2 plus invariant should be positive on both sides. This already tells you or justifies my previous assumption for Seiberg-Witten theory that the global B2 plus invariant should be bigger than 1. Now it will be definitely bigger than 1 because these are two non-positive integers. And that will buy us the following, that these maps will just be 0. And now what I would like to do is to define a map from here to there. And what do? I just take this map and I notice that if I take the generator here or an element G here, if I do it twice, then I get to the 0 element, which means that when I take its image, this is in the kernel of that map. But luckily this is exact, so let's call it F. So this is X1, X2, Fx1, this is Fx1G, this is in the image of some element Y. And I can apply the Fx2 to Y, and this will be my invariant associated to this 4 manifold. And you should notice that we use the fact that this is 0, which follows from that assumption, to actually go to here. And then this assumption will come into play by saying that it doesn't matter which inverse image you take. If you take a Y prime, then their difference will be 0 here. So they are in the kernel, so they are in the image. Y minus Y prime will be the image of Z. And if you go around, it just tells you that this is the same as Fx2 Y prime. And my plan was to take this 4 manifold invariant and show that it's non-zero for a symplectic manifold by using the surgery triangle. I will not do that today. Maybe I will not do that ever, but we don't know. But so that would be sort of the counterpart of the adjunction formula. The adjunction formula, the adjunction inequality I tried to prove in the morning, gave you a relation between basic classes and the genera of surfaces. And this argument would show that the first Chern class of a symplectic manifold always has a non-zero invariant. And that helps you to sort of make estimates on this genus. This is the end of my torture. And tomorrow morning, I would like to do more of like topology, finding surfaces in four manifold, encountering four manifolds, and bringing up puzzles. So that's for today. Thank you.
So to the exact triangle, I have like alpha, beta, gamma, and I go from like, if I go from alpha, beta, gamma, and instead of I go alpha, gamma, beta, do I get an interesting map if I compose like from y alpha to y beta back to y alpha?
So you don't choose the order. You don't, I didn't really understand, but you go from alpha to beta to gamma,
Yeah,
but you cannot go in the other order.
I see.
So you remember these F's and H's? F was a chain map, H is not. It's a chain homotopy. It respects the module structure, but not the boundary map. So you can't go backwards.
Sorry. Can we probe the surgery exact triangle in Z coefficient?
Yes.
I see.
Well, I didn't talk about Z coefficients. It was always, F was always conveniently chosen to be the field of two elements, but it has this refinement. And it has various refinements. Like I didn't talk about, these groups are not only groups, but they are graded groups. And the grading is a complicated issue here, depending on the spin C structure, whether it's a torsion or non-torsion spin C structure. And we can say something about the grading, but these will not be grading respecting maps. They will just sort of blow out, a grading A will, the image of a grading A element will have various different gradings. So it's not homogeneous. But it's a triangle. So it's very compact, very short, but it doesn't have maps which respect the grading.
Question?
So the
Yes.
environment you constructed is a map from HF minus of S3 to HF plus.
Yes. So of course, I mean, this would be pointless if we don't know what these groups are. But these groups are very simple. This is just, this is just FU. And this is just FU, U inverse over FU. So we can just take the generator here and see where it lands. And of course, if you do everything mod 2, you don't get very exciting information. You can say that it's 0 or 1, but when you run the whole business over the integers, then you get an integer. And I didn't say that, but in fact, you should do it everything in the spin C refined category, and then you get an integer associated to a spin C structure, exactly like in the Cyber-Witten case. So somehow the philosophy is that in the Cyber-Witten case, you sort of keep the manifold intact, and then you sort of pick all kinds of bundles and constructions and differential geometry there. Here you sort of slice up your four manifold. And this is why this theory is much more suitable for surgery-related problems, while Cyber-Witten theory is probably for like these global structures, like which manifolds and with positive scalar curvature or something like that. Yes?
Why does this condition of the B2 appear?
So this will guarantee that these maps are 0. If B2, so there are two options for this B2, right? B2 plus, either positive or 0. If these terms are zero, then these maps are isomorphisms. And then my argument of like how to go from here to there breaks down because this is not zero, and why is it unique breaks down because this is not zero. So this is how this condition appears in that setting. And there's this message. So the theory seems to be very sensitive of the distinction between B2 plus equals 0, B2 plus equals 1, and B2 plus bigger than 1. And you might say that this is the flaw of the theory, and I object. This is the condition under which we study four manifolds. Four manifolds with these three types of B2 plus are very different. A little bit like when you study Riemann surfaces, there are like three categories. There is the sphere, there is the torus, and all the rest. And this is somehow reminiscent to that. The B2 plus equals 0 guys are like the sphere. We know some things about those. B2 plus equals 1 is a little bit like the torus, and then we have all the rest. And I hope that this, of course, I didn't argue why this map is 0, but suppose you believe that, that this condition implies that those maps are all 0, you see that in this picture, it's a necessary condition. And this is built in for manifold topology. So if somebody approaches you with a TQFT, which computes all the interesting invariants, but completely disregards B2 plus, don't buy it. Just don't. Okay?
And the map is independent of the choice of the slice Y.
Say it again.
Is the map independent of Y?
Yes, of course, you know, so there are further choices here. I took a slice up of the four manifold. You should prove that it doesn't depend on that, and it doesn't depend on this slice. Of course, there should be some condition under which it holds. The Y should satisfy some conditions that the spin C structures are partitioned properly. So under reasonable conditions, it's independent of the choice of Y, of course. Actually, in all practical cases, you will get exactly what the cyber-Witten invariant tells you. And whether this has been a theorem or an expectation, I don't know. Probably it's very close to be a theorem. So the homology groups appearing here and in cyber-Witten theory are proven to be isomorphic. The maps induced by cobordisms are not yet, but because of lack of interest or enthusiasm or endurance, I don't know. Okay.
No more questions?